In this video, I'm going to talk about how to balance chemical reactions. So this is an essential step when we're going to try to figure out how much of one material is going to produce how much of another material. And the chemical reaction describes the number ratio in which they react. Later on, we'll deal with how to deal with the mass of each product and reactant and how they're related. Okay, so we're going to do a few simple examples and describe a little bit of the terminology. So, first example is going to be carbon, graphite, burning, combustion means combination with oxygen. Molecular oxygen is a gas, so I'm going to give you a little picture here of these two blue oxygen atoms. So it's a diatomic molecule and a gas. This is a solid. Now solids generally have an infinite size, and so when you look at the formula of a solid, you usually see just the symbol of the element if it's a single element, or the simplest integer ratio if it's some sort of ionic compound. If you see something like P4, that tells you something interesting about that particular element, and that it exists as P4 molecules. But since it's a solid, it's a bunch of packed P4 tetrahedral molecules all in a regular lattice. So G stands for gas, S stands for solid, L stands for liquid. Another type we're going to do is AQ for aqueous solution. So some things dissolve in water, and then how they exist inside of water solution is called aqueous. And of course, we're going to denote the before and the after as an arrow. So these are called the reactants, and this is called the product. And then the arrow means yields or gives or produces. Those are all synonymous. Sometimes you might see a little delta symbol above the arrow, and that means you need to heat to get this reaction to occur. So delta stands for heat. All right, so conservation of matter must be obeyed. That is to say, we must have the same number of atoms before and after we finish. And so what this equation says, and it's already balanced, is that one carbon atom over here becomes one carbon dioxide over here. So you can see one atom, one atom. Okay, so however many carbons you burn, that's how many CO2 molecules you get. Not only that, but for every carbon you burn, you combine it with two oxygen atoms, and you get CO2. Now that's assuming a lot of things like complete combustion and so on, but you can see that the number ratio is 2 to 1 for carbon and oxygen, but it's 1 to 1 for the solid and the diatomic molecule. Okay, so but we have the same number of atoms of carbon on both sides and the same number of oxygens on both sides. Now let's look at an unbalanced equation. So tetrahedral phosphorus plus the diatomic molecule bromine, which is a liquid, goes to PbR3. Now this is not balanced. There's not the same number of atoms on both sides in the way we've written the equation. So the first thing to think about is, well, if there's a 4 here, I can put 4 here, and now I have the same number of phosphorus atoms, okay? You cannot change these numbers, because if you change these numbers, like if you put a 4 here, it's a different molecule. P4Br3 would have a different Lewis structure than PBr3. As a matter of fact, P4Br3 is not a molecule at all. So you can only change the numbers out front. All right, well, once you do that, now we have to consider the other element, which is bromine. And we have 4 Br3 molecule, PBr3 molecules, and that's a total of 12 bromine atoms. So in order to get 12 bromine atoms, I need to use 6 diatomic bromine molecules, and now this is balanced. Of course, you should always check and make sure that the numbers are balanced. There's 4 phosphorus, 12 bromine, good. All right, so you should know how to count the number of atoms based on coefficient out front, which you're allowed to change, and then the subscripts within the formulas of the compounds, which you're not allowed to change. All right, so another example is the Thermite reaction, which takes solid aluminum powder, combines it with rust, iron 3 oxide, and they're both solids, you ignite it with some sort of source, and so this requires a little heat, and it gets so hot that the iron produced will actually be molten iron, and then of course the aluminum oxide. And so what happens here is basically aluminum is taking the place of iron. So aluminum's pure metal here, iron is in the oxide. Now iron is the pure element, the metal, and then aluminum is in the oxide. That's how thermite works. So it doesn't use oxygen from the air, it uses oxygen from rust. Okay, so let's look and see. Got one aluminum, two aluminums. So let's try that. Okay, aluminums are balanced. Now what about oxygens? I got 3 and 3, so those are oxygens are balanced. Let's try iron. 2 irons and 2. So what this chemical equation says, 2 atoms of aluminum, or 2 anythings of aluminum, and 1 unit of iron 3 oxide produces 2 iron atoms and 1 formula unit of aluminum oxide. All right, so in most cases you would balance element by element. However, there are some cases where it might be convenient to just balance ion by ion if you have ionic material. So let's look at this one. This is sodium phosphate dissolved in water. Okay, and what this means is that there's some sodium ions floating around, surrounded by water, and one big old phosphate group for every 3 sodium ions. Big old blob. And the rest is just all water around it. Magnesium, dication, and then a chloride and a couple of other chlorides over here, so maybe. So what this equation is saying, I have a solution with these ions dissolved and another solution with these ions dissolved. I'm mixing them together, so now these ions can look at these and these can look at these. So what we need to do is figure out, okay, there's maybe new ion combinations that are possible. So here, sodium cation combined with phosphate anion, that was the only positive-negative combination possible in this solution. And this is the only possible combination in this solution, magnesium 2 plus and chloride. However, once I mix them up, now magnesium 2 plus can see phosphate, and sodium can see chloride. Okay, and so that's what this reaction is saying. So this is a double replacement where we say, okay, maybe new pairs of ions can move around. And so let's look at the balance. We've got 3 sodiums, 1 sodium. Okay, but it's probably not a good idea to start balancing something right away. Usually you want to start with the most complicated looking one first. And so the most complicated looking one to me is magnesium phosphate. All right, so if there's 3 magnesiums here, let's try 3 magnesiums there. And that gives me 6 chlorides. So if I have 6 chlorides, I'll have 6 sodium chlorides. And now if I have 6 sodiums, I have 2 of these. And now let's look and see if the phosphate's balanced. 2 phosphates, 2 phosphates. Everything is balanced, okay? So it might be more convenient, rather than balancing phosphorus atoms and oxygen atoms, if you recognize that the only place that phosphorus atoms and oxygen atoms appear is as a group called phosphate, then all you have to do is number of phosphates, number of phosphates. So it doesn't have to be strictly atom to atom when you're balancing things, as long as you have group ions that stay the same as they are.